The guy on the YouTube channel, What If I Did This, he was using a round aircore RF based low frequency resonator coil. So what I've done is I've modelled a rectangular based system. I'll explain why. Where a round core coil is quite common, there are some disadvantages to a round coil, in that the field itself becomes more what's the word? It becomes like the field becomes less directional. It doesn't travel quite as far as a rectangular coil in directional means. And anyway, so this is what I modelled. It's pretty big, so I had to adjust my dimensions to accommodate the wire which I've ordered, which actually arrived this morning. Let me see if I can just show you my wire. So this is oxygen free copper, and it's transparent. Let me see if I can get it out of the bag a bit. So this is high grade speaker wire. It's actually 8mm in width from the from one side to the other, so it looks about the same kind of wire that the other guy was using. The good thing about oxygen free copper is it has it's less prone to what's the word? I can't think of the word. Can't think of the word. My brain's gone to mush. There's what's the word? I can't think of it. It's just less prone to noise anyway. There's a certain thing that happens with RF frequencies at higher speeds that causes anomalies, parasitic, that's the word. So it's less prone to parasitic elements in the signal. So anyway, I actually got 20 meters. I think there's 20 meters in here. Or was it 10? I can't remember now. But anyway, there's enough there. So I made that bobbin, which I'm just showing you on there, the right width to accommodate 9 turns, which is what I actually printed his diagram out, and I wanted to talk about that a bit. I'll put it on the wall over there. Sorry, it's a long way away, you can't really see it over there. There were some issues with the diagram. I'm not going to go grab it right now because, maybe I can load it on my computer. Just a minute, see if I can find it. So, I'm just printing the bobbin right now, actually, on the 3D printer, so that's going to take a while. Let's see if I can get this up on computer. And then I can show you a bit easier on that. Right, so this is his diagram that he did. Okay, so so one of the problems with this diagram, and I was a little bit in awe when I was looking at it, because I immediately spotted some issues. If you look at these connection between his 180 turns and his light bulb, the light bulb that's at the bottom there, it's actually connected directly through that coil. That coil goes round to base of the transistor. I've messed up the focus now. So when he was connecting his light bulb on when he was doing his tests, his current consumption went way up. And initially, when I was looking at his YouTube videos, I'm thinking, well, hang on a minute, this doesn't make sense. I mean, he's connecting all these other coils, and his other coils have got a load, and he's moving them in and out of this field. and the amount of consumption he was getting on all of his LEDs made no difference to his input current. That's what gave me the that inspired me a little bit. That made me think, well, wow, this is pretty cool actually, that if you can actually provide power to all of LEDs and not see an increase on input current, that's really good. But when he connected his 240 volt 9 watt LED, his current went up. Initially I couldn't understand why, obviously because I studied his diagram, but then I realised what was going on. When he disconnected his 9 watt LED, his 180 turns coil, which was driving the base of the 2N3055, had what's called a floating ground. It's basically connected to the ether, as in RF ground. It was floating. It's a floating ground which can actually move anywhere. It can move, its potential can be completely anything really. Instead of being 0 volts, it could be minus volts, could be plus volts, it could be anything, because it's floating ground. Well, you don't want that situation if you want a stable circuit, and it also changes the frequency as well. So having a floating ground on an oscillator circuit, which is what this is, it's a very basic oscillator circuit. I have built RF circuits before in the past, and I know that they can be extremely unstable, and what's quite important is to have them stabilized. And one of the best ways of stabilizing them is to have a biasing resistor between the base of a transistor like the 2N3055 and ground. So you'd basically connect a resistor of probably 1K or 200 or 330 ohm, depending on the impedance. It depends on what the impedance is of the circuit, but you would have to impedance match the base to the emitter. So you'd have a resistor basically between base and emitter of something like 1K, or you could have higher. It depends on the impedance, what you want to use as the impedance. So if you're using 1 mega ohm biasing, impedance, then you would have a much higher value between base and emitter, something like 500 kilo ohms or something like that. But anyway, I looked at this and I thought, well, there's no wonder his current was going on when he connected his light bulb, because he was directly driving extra power into the base of the transistor. So most of his power was going through the base of the transistor, right? So ideally, you don't really want to be using you don't want to be direct driving an output or a load on across between base and emitter through a coil. You know, that's not the ideal situation to be doing. Now, when he took the bulb out, it continued oscillating, and he had issues sometimes where it would stop oscillating. And it's obvious to me why that was happening, because if his bulb was not connected to emitter or ground, referencing the transistor, if his bulb wasn't connected, then as soon as the field collapsed on the 180 turns 1 wire, multi-strand wire, to the base of the transistor, as soon as that field collapsed, then that coil would effectively become 0 volts, or there would not be any potential voltage on it whatsoever. And the only way it could get his oscillator to start was to arc something, was to spark something. And that obviously makes sense, because when you do that, you induce a reactive current in the 180 turn coil, which would pulse back to the transistor to start the oscillation process. Now, one way of solving that problem is to have a resistor between where the bulb normally is. You've got the 9 watt bulb. What you would do is connect a resistor in parallel to that bulb, but you would have the resistor connected permanently to it. So between emitter and the other side of the LED bulb, the 9-watt LED bulb, you would have a resistor in the value of something like 100k, right? You'd have a 100k resistor across that, and ideally a 10 nanofarad or 100 nanofarad ceramic capacitor. Ideally ceramic, because ceramic works better with RF. It doesn't. You don't really want an electrolytic in there. You want something like an ceramic disc, or you want even a polyester capacitor would work at lower frequencies. So if he had that capacitor in there, so that when you took the bulb out, when you removed the 240 volt 9-watt LED, if you took that out, it would still continue oscillating. It would continue to oscillate because it would still have a circuit there even when the bulb wasn't there, but it wouldn't draw a lot of current through a high value resistor. It would just maintain the oscillation, so he wouldn't have to keep sparking his device when his bulb wasn't in place. But the actual resistor wouldn't consume any mean watts really. It would probably be a few microamps or microwatts. It would be very small, but it would be enough to sustain the oscillation of the transistor. So anyway, I've been studying it, and I looked at it, and I thought I could see a few errors, a few problems with that design. But you would obviously you would need to experiment with the value of the resistor between the emitter and the 180 turn coil. You would actually experiment to find the best value resistor really, because it depends, as I say, on frequency, because higher frequencies don't work well through a resistor. So you would need to capacitor in parallel with that resistor, a small value across it. And so that if you did put the bulb in, which is I'm not recommending though, because as I say, it's not, you're not supposed to have a load directly connected between base and emitter really, which is what this is, through that coil. The load, from what I understand, is aircore. It's a separate coil, completely separate to this circuit. He's just got his coils, and then he's got a capacitor across his coil, and he's moving it around in the air, and it's not actually connected physically to this circuit. It's actually purely aircore. So anyway, I wanted to let you know that I've actually got my wire. So yeah, it looks like the same stuff that he was using. As I say, I made some adjustments to my, I'll take that down now, I'll just take, how can I get out of this? I need to press the escape button. Right, so I'm zoomed in a bit, sorry about this, it's probably a bit wobbly. As I say, I just closed my other window as well. So my bobbin, so that's my bobbin. I'm printing this in 2 halves, and I'm going to join the 2 halves together, so let me just show you that. So I've got hang on a minute. Right, so I split my bobbin in half, so I'm printing 2 halves and joining them together. It means I can print it without support material, because I can print it that way up, you see. So I'm going to print those 2 halves, join them together, then I can wind my coil on that, and then I'm going to work on I've got to work on a stand, like an antenna array, to hold all this stuff together, and I'm going to mount it vertically, sort of like that, you know. I can't get it. It's going to be horizontal, like that, I mean. And then I can have a plastic bar. Sorry, I'm shaking my hand now, I can't keep still. So I'm going to have a horizontal beam, basically. I'm going to make a short one. It'll be probably 24 inches long or something like that. So I've got to model that in SketchUp. I haven't done it yet. I haven't got it there yet, but I just thought I'll just get this made first, because I can make that on its own and just test it freestanding, you know what I mean, without any... I need to zoom out because I can't keep my camera still. Anyway, right, so anyway, that's going to be 6 hours to print that half, another 6 hours to print the other half, and so I just wanted to give you a little heads up on what I'm doing at the moment. But at least I got some of it. I also ordered a watt meter. I thought, let's be consistent. So I've ordered a watt meter, the same as what if I did this has, exactly the same model as what he has, so that we can actually do some direct comparisons. As I said, the only difference between I'll explain what I did with my coil former, you know, because I made it oval shaped. What I did was I took the dimensions from my spool, which I have the same as what he has, the circumference. I took a tape measure, I measured the circumference around the round bobbin holder, and then I basically flattened it out by using my tape measure to make an oval shape at the same measurement. So the tape measure is the same length in the oval shape as it is on the round shape. By doing that, the wire's the same length, and I can also keep the number of turns the same as well. So it's 9 turns, as I say, for that primary coil. Anyway, yeah, I'm trying to get the energy up to get this done, and we'll get there eventually. So that's just where I'm at the moment. Okay, I'm going to go and watch some more snooker. Yeah, it's pretty cool actually that Luca Brissell won the final. His first time he's ever won a final in Belgian Bullet, his nickname is. Pretty cool. It was quite something to see. Anyway, I'm getting off track. I'll see you later, and I'll keep you updated when I have some more news.